Ready? Okay. Thank you all for coming. My name is Hari Pulapaka. I'm a lead program manager in the Windows Core kernel team. So part of my responsibilities are I own the core software aspects of the kernel. I work on things like the CPU scheduler, process, thread management, the memory management, and along with all of that, I also own part of the background multitasking infrastructure in Windows. And sure. So part of that, I also own the core multitasking infrastructure of Windows. So that includes things like suspend and resume implementation, and how to run in the background and using background task, which is basically what this talk is going to be about. So before I even go in there and talk about background task, can I have a quick show of hands to see who knows about background tasks, who's written a background task, and who's like actually written the doc? Okay, that's pretty good. That's almost 50, 60% there. So in this talk, I'm going to have some pretty basic hello world background task demos. So a lot of you who already written background tasks, have used background tasks, may not find it all that useful. But there's going to be enough in-depth content also, which will be useful for the more advanced developers. So there'll be some examples of the kind of gotchas that we've seen people, like the kind of mistakes that we've seen developers make. What is the impact of these mistakes on the system? What is the battery impact, and what is the power impact of these mistakes? So it has so the talk will have a little bit of something for everybody, I hope. And so I'm going to have maybe 5-10 minutes at the end for your questions. So if you do have any questions, try and hold them towards the end, and I'll try and answer them at that point in time. Okay. So let's get started. So agenda. So today's talk, I'm going to be starting at a very high level. I'll give you a very high level overview of what the model is, the whole running the background model inside Windows is. I'm going to show you the basic architecture of how background tasks are implemented inside the system. We'll talk about the whole services that actually implement the background task infrastructure. And then I will try and dive deeper into the code, and I'll do some 2 demos. One will be a pretty basic hello world background task, and the other one will be debugging a background task. And then I'll talk about connected standby and what it means to have background tasks and connected standby. And then finally, we'll talk about what's new in Windows 8.1 and end the talk with a pretty short list of best tips and practices. And before I actually go ahead, I wanted to call your attention to the picture on the slide there. The picture on the slide actually shows things like Skype. It shows mail. It shows your messaging apps. And this picture is by design. I purposefully put this picture in there to call out the fact that apps like Skype, Link, Mail use background tasks to show your VoIP call, to download your mail in the background, to perform all these features. So the APIs that we have for background tasks are the same APIs that Skype uses. It's the same API that the communication apps use. So you get to use these same APIs. There is no secret sauce in there. They use fully documented APIs that are already on MSDN. And so using these same APIs, you can build as powerful experiences as apps like Skype, like Link, and Mail. Okay. So the background multitasking model. When we first started sorry for the echo, I guess. When we first started on Windows 8 and we decided to think about how to implement the whole app model, one of the core fundamental guiding principles of us has always been we want Windows 8 to have a consistently great battery life. What that means is if you install 1,000 apps tomorrow, your battery shouldn't suddenly suffer. If you just have one app on your system, your battery should be the same. If you install 1,000 apps in the system, it should be more or less the same. And so that's why when we designed the whole app model in Windows 8, what we did is we did suspend and resume. So when your app is on the screen, it is able to use the full resources of the system. And when your app is not on the screen, it has no pixels on screen, we suspend the app. And well, when we say we suspend the app, what that really means is the CPU does not schedule the app anymore. The threads of the app cannot run any code. However, the app continues to remain in memory, but it does not take any battery resources because obviously it's not running any code. That means it's not doing anything. Now, if you think about it, once an app is suspended, there are going to be enough scenarios that people are used to when they use Windows that actually need app to run code. And so how do these scenarios work? And so what we did is we took a very scenario-focused approach. We decided, like, once an app is suspended, we said, what are all the scenarios that people care about? And we made a list of all the scenarios. And then we designed APIs or affordances in our internal lingo for each of those scenarios. And so, for example, the APIs are live tiles. In live tiles or scheduled toast notification. In all of these APIs, you don't actually have to write any code. The app doesn't have to be running. The app could be suspended, terminated. However, your tile is updated using the Windows notification service to show the latest status or the latest weather or the latest updates. And Craig Brocksmith has a talk called Alive with Activity, where he talks a lot about all of these things, and he shows you how to write the ideal tile app, how to show the best performance out of your tile, and how to do the right UI for those things. And then finally, we have background tasks, and which is going to be the thrust of this talk. And background task is where the app actually needs to run code to do some work in the background. And that's when you really want to use a background task. So a basic short introduction to background tasks. Like I already said, background tasks are usually required when your app has to run code. The background task is meant to be a short running thing that it does some work and then goes away immediately. Background tasks are not meant to be long running or services. We don't have services in the Metro app. The way to typically think about a background task is it has a system provided trigger, and when the system trigger is fired, your background task runs. And when you run, you basically get to do a little amount of work, and we have resource quotas on the background task that see how much CPU you're using, how much network you're using, and if you exceed those quotas, we suspend the background task. And all of these things are designed primarily so that you can support all of the scenarios that you already expected inside Windows for its entire history. And however, it also ensures that you have a consistently great battery life because we have pretty solid resource quotas around the background task. So even if you have poor code, it is not going to impact the system because we are measuring what kind of activity you're doing, and when we think your activity has gone beyond a threshold, we'll suspend you. So what can you do in a background task? Pretty much everything. A background task is just your own app code. There's nothing special about a background task. It runs within your app, the same app container as your app. It runs in the same user credentials. So whatever your app can do, whatever your app can access, any files that your app can access, any capability your app has, the same capability exists with the background task. So there's nothing special in there. However, there are some caveats to that. A background task cannot access audio or video for obvious reasons, right? If you allow a background task to access audio or video, you could have a background task that suddenly comes up and starts like snooping on your conversation. So there are some caveats in there. The other caveat is that a background task cannot bring your app to the foreground. So in the new store model, we don't have any sort of Win32, the old desktop app style concept called set foreground window. So you cannot actually bring yourself to the foreground, and a background task cannot do that. The background task can do certain UI updates, such as updating a badge or updating a tile or showing a toast or a notification. And in fact, this is exactly what we want your background task to do. And like I mentioned, a background task has a set of triggers that are provided by the system, and when the triggers are fired, the background task runs. So examples of these triggers are something like control channel trigger. A control channel trigger is a trigger that is used by VoIP apps or even mail apps. And so these apps need a long-lived socket connection to the server. And what happens is that if your app is now suspended, your socket connection still needs to be active, right? But we don't want the app to be always running because that would defeat the whole purpose of suspend and resume. So we have this thing called control channel trigger. What the control channel trigger is basically you will write a background task, and inside the background task, you will provide a socket. And that socket is is listened to, I guess is the word we use. That socket is listened to by the Windows networking layer. And so when your app is in the background, it is suspended. And if you receive an incoming packet on that socket, for example, your VoIP call or your push notification from the Exchange server, Windows is listening on that socket, and it will say, aha, so this socket has some incoming data. So let me go and launch the background task that is associated with this trigger. And that will be your background task. And we will activate your background task, and then you will read the packet, and you will display a notification to the user, show the VoIP call, download the mail, or whatever your app has, whatever functionality your app needs to has. The next two triggers, device use and device firmware and device servicing, these are two new triggers that we added in Windows 8.1. These triggers are primarily used for USB and Bluetooth device sync. They are used to either sync content, or if you want to update the firmware on a device, you have to use these triggers. And then the next trigger that we have is a location trigger. This is also a new trigger inside Windows 8.1. And this is used primarily for geofencing style application. You provide a location, and you say, I need a fence around this location. And when your device is within that location, then your background task is triggered, and then you can get to run code. And at that point, you can probably show a toast or whatever your app decides. If you want to show an advertisement or a reminder that says, hey, you're near Safeway, why don't you just buy eggs? I don't know. Whatever is the reminder that you want to show. The next trigger is maintenance trigger. This is a trigger that was always there since Windows 8.1. This trigger allows an app to run code in the background only when the system is on AC power. So this trigger does not have that much of a battery impact on the system. And because it does not have that much of a battery impact on the system, this trigger is available to all apps. The app does not need to be in the lock screen to use this trigger. The common examples of apps that use this trigger are apps that try to renew their Windows notification channel. I don't know how many of you have used Windows notification service, but the Windows notification service has a channel that connects to the server and to the app. So this is a per app channel, and this channel expires every 30 days. And so people generally use, app developers generally use maintenance trigger to renew their channel after 15 days or 20 days, just so that they have enough time before it expires. Push notification trigger is the equivalent of control channel trigger for Windows notification service. It has the same purpose as a control channel trigger, but it is tied to a Windows notification service. So this allows you to run raw notification triggers. So if you have an incoming push email via the Windows notification service, your background task is triggered. You get to run code, and you can sync mail or update status or whatever is the functionality you need to implement. System trigger is a grab bag of triggers inside the system that we think are useful for app developers. This exposes certain system conditions that we think app developers may care about. For example, internet available, or user present, or user away. So these triggers, whenever for example, the scenario is if you have a link app or an IM app, you probably want to change the status of the user on the server side to user away when the user locks his machine or walks away from his machine. And so typically how apps implement this feature is by using a system trigger, and the trigger is user away. And so when the user moves away from their machine, locks their machine, this trigger is fired, and your background task runs, and then the link app basically updates the server side to say user Hari is now away, and so all your friends can see your latest status. Time trigger is your standard periodic trigger. It allows your app to run code periodically. And the least count of a time trigger is 15 minutes, and that means your background task can run no sooner than 15 minutes. The most common use cases of this are for apps that want to sync RSS content in the background, or POP email clients. I don't know how many have POP email clients anymore, but that's an example. And the final column in there is the lock screen required or not And I'm going to talk a little bit more about the lock screen thing on the next slide. But before we go to the next slide, the other thing I wanted to call out is system trigger has a mixed status. Some triggers inside system trigger do require lock screen access, some don't. And we've done that for a reason, because we wanted to make sure the most frequently occurring system triggers do need lock screen access, whereas system triggers that are not very frequent, for example, session connect or session disconnect, they don't need lock screen access. So lock screen. So anytime I talk about background tasks, I think one of the first questions people ask me is, what is up with the lock screen? All I want to do is run my code and download my RSS feed or sync my content and go away. Why do I need to be on the lock screen? Or why does the user need to see a yes? So fair enough. So hopefully I'm going to explain to you why we have this coupling with lock screen and background tasks. And maybe that will explain to you why this design exists. So background tasks are designed primarily to have real-time content. So that means as soon as you get a push email, your background task immediately runs. As soon as you get a wipe call, your background task immediately runs. And so, as you can imagine, there is no bound on this. It's all dependent on the user. For example, a user who has a very heavy email server could receive 100 emails a day, whereas the average mom and pop will probably get 10 emails a day. So there is no upper bound here. And so that's why the impact of a background task could be extremely high or not that high. And so that's why we have this coupling between lock screen and background tasks, is so that the user actually is aware of all the background activity that is happening on the system. So we don't want a user to be surprised when you suddenly install, like imagine if there was no lock screen and every app is allowed to run background tasks in the background. And so the user won't even know what is running in the background. Yes, we have Task Manager, but really, not a lot of people know about Task Manager. So most people don't know what's happening in the background. You might install 100 apps, and suddenly your the average battery of your device goes down. And so there is no way a user knows what is going on. So by having the lock screen and asking the user, is it okay to allow this app to run in the background or not, we are forcing the user to have some control over what apps are running on your system. And if the user does notice something bad happening, they have full control by just going back to the lock screen and removing the app from the lock screen. And that basically means they can't run their background tasks anymore. The other reason that we need to have lock screen is it forces us to have an upper bound on the amount of background activity a system can have. Imagine if there was no imagine if lock screen had 100 limit, had no limit on the number of apps. In that case, how do we ever know how much background activity can happen on a system? We have no idea how much background activity happens in the system, and you could install 100 apps or 1,000 apps, and all of them could be running in the background, and your device battery life would just suffer. And so by having 7 apps on the lock screen, it allows us to have a maximum upper bound on how much background activity you can have on a system. And so this is a very high-level architecture overview of how this whole system is built. I'm obviously going to gloss over a whole lot of details in here, so you may find it useful, though. So when a user is using, so if you look, as you'll see in the demo that's coming up, to use the background task, you need to use the background task builder class, and you need to register your background task. You need to provide a class name, you need to provide a trigger, and you need to provide your your conditions. And so what really happens in the background there, or underneath the covers there, is that the background task implementation is done as a DLL. So our DLL is taking all of this information and is registering your class name and your trigger with the background task infrastructure. The background task infrastructure maintains a database. The database is a pretty simple map. It has your class name, and it has which is your entry point, and it has your trigger. And so anytime your trigger is fired, your class is launched. And the triggers basically are hosted inside services. And it's these services that are providing the concept of a trigger. These are the services that are launching the trigger. So for example, if you see in the diagram there, you have the time trigger service, you have the system event service, you have the location service, you have the WNS notification service. And so these are what we call in our internal lingo as brokers. These are the people who are really trying to provide the functionality that your trigger implements. And so what happens if you have an incoming packet, the control channel service is the one who's actually listening on your socket. And so when there's an incoming packet on that socket, control channel service says, hey, somebody is listening on this socket. And so he's going to activate that trigger. And when he activates that trigger, background task infrastructure is actually listening on that trigger. And it says, aha, somebody activated this trigger. Let me go look up in my database, who is this guy who's waiting for this trigger to get fired. And inside our database, we'll see that this is the app and this is the class name. And we'll launch that class, and then basically your background task runs. So that's pretty much at a very high-level overview of how this thing is built. I'm glossing over a lot of details around how we are doing resource accounting, how we are counting how much CPU you used, how do we unsuspend an app, how do we resume an app, because that's not all that useful, I think, to app developers, because it's mostly an implementation detail. Okay. So with all these concepts done, I think we will now try to go into a little bit of the code. So background tasks can be authored in any Windows runtime language. It can be in C#, it can be in JavaScript, C++. The other interesting aspect there is that the background task does not need to be in the same language as your app. It is completely decoupled from your app. So your app could be written in JavaScript, it could be written in C#, but your background task could be in C++ or JavaScript. And in fact, that is pretty much the model that the communication app uses. Their whole UI, the mail app UI is built in JavaScript, but the background task of the mail app is written in C++. And notice the key phrase in there, Windows runtime language. So I will talk more about it in the demo, but that is a point you should remember when we get to that. Background tasks must be manifested, so you need to have something in your manifest that specifies what is your class name and what is the background trigger that you're using. Background tasks must also have to use the background task builder to register their background task. Now, if you think about it, there seems to be some sort of redundancy here. Why do you have something in the manifest, and then at the same time you also have to have the app run and register the background task? Why can't the manifest just automatically register the background task? So the reason for this is twofold. The reason we have the manifest is that it allows us to statically understand what are all the background tasks an app is implementing. So we never even have to look at the app code. We don't have to run the app even. All we need to do is just look at this manifest, and we can know that this app is using background task foo, and it's actually using the trigger system, time, or control channel, or whatnot. So this is pretty useful for us in terms at the store, because it allows us to validate, and maybe we can do some extra tests if an app is implementing some background tasks and run some extra checking on the app to make sure that everything is working perfectly. The other reason we need the manifest piece is that when you think about it, a background task, the entry point or your class at the base layer is simply just a COM class. Like you probably don't have to look at all of this goo, but when you implement a COM class, what you need to do is you need to provide a class ID, you need to provide a host name, you need to provide an executable, and this needs to be registered inside with the COM infrastructure so that COM can launch your class properly. And so when you write your background task in the manifest, all of this goo is happening in the background automatically. What we do is we actually go register your entry point with COM so that COM knows what this class is, what is the class ID, generates a GUID for it, and it generates a host executable and all of that. So all of this is happening in the background, and that is another reason why we need manifest, why we need entries in the manifest. A background task can have exactly one trigger, like I already mentioned. It can have 0 or more conditions. And a background task will not run until all of the conditions are true. Now, conditions are a very interesting and powerful feature of background tasks. An example of a condition, or an example of a background task with a condition is, I have an app that wants to do some work when the user is not away, but there should be internet available. Internet should be available because I'm going to go download some content. So in that case, what I would do is I would use a trigger, maybe a time trigger that says run every 1 hour, but I want to make sure the user is not there and I want the internet to be ready, to be available. So I will add a condition called user away, and I will add a condition called internet available. So that means even if your time comes, like let's say you say I have a background task that runs 1 hour from now. Even if the time comes, 1 hour passes, your background task will not run until all of the conditions are true. So that means until you have internet available and until the user is away. This allows you to do away with the tedium of code. So this allows you to, for example, always assume that when your background task is running, you have internet. You don't have to worry that, oh, can I talk to Bing.com or can I talk to Google.com or can I talk to CNN.com? No, because you use the internet available condition, you should just assume that you have the internet there, and you should just go ahead and make all your network operations. And so that's why it's a pretty powerful facility. The final point is something that I don't know how many people are aware or can understand easily. Background task registrations are persistent. Persistent basically means we are storing your background task registrations inside our database. Remember at the start, at the architecture diagram, I'd mentioned that basically the infrastructure is maintaining a map. And the map is, at a very basic level, it's your class name and your trigger. And so we store that in our database, which is in persistent storage, backed by a file. So why is this important? So if you think about it, this is important because let's say you have a background task that says, run me from 1 hour from now. And at point 20, the system reboots for whatever reason. And system reboots, and then the user logs in at time 21. Now, at this point, your task is not running. Your app no longer is even there. So when time 60 comes, we will automatically launch the app. Your app doesn't even have to be running. It doesn't even have to be suspended. It doesn't need to be present at all. We will just launch your app. We will just launch your background task. And that is why when your app is again brought back to the foreground, and trying to register another background task, you should ensure that you haven't previously registered your background task already. Okay, maybe that was not very clear. So a background task will stay registered in our database until it is triggered, or you actually call delete on the background task. So that's why next time your app launches and you want to register the background task again, you want to query with us to see if the background task is already registered or not. And to make that query, we have the enumerate all tasks API, which will allow you to give you all the background tasks that are registered with us. And so now we come to a demo. So this is going to be a pretty basic Hello World demo. And in this, I'm going to be talking about how to add a simple basic background task to your project. So this is an empty XAML project. It has one button called Register Background Task, and it has a text box where you can display text. And that's pretty much it. It doesn't really have a whole lot of stuff in there. And if you look at the XAML part here, preview builds. Okay. The demo gods. All right, I'm not going to click that button again. So let's right-click on your project, and let's say we want to add, let's right-click on your project, and we want to add a class library. And you choose the class library, Windows C#, and let's call it your background task lib. Okay. And that's it. We're going to add background task, and this is your background task. And so to use a background task, you need to implement the iBackground task interface. And to implement the iBackground task interface, you need to use the Windows application background namespace. And you implement the iBackground task interface. And so right-click on this one, implement interface. And that's your background task. And whatever is your implementation of your background task goes in here. And now here's the key part that I think a lot of developers are tripped up on the first time when they try to use background task. A background task is a Windows runtime component. What that means is you need to change the output type of your background task from a class library to a Windows runtime component. If you don't do this change, then we cannot activate your background task, because remember, a background task at the end of the day is just a COM class. And so when we try to activate a COM class, it needs to be a Windows-specific thing. It cannot be a .NET class library. And so this is how you do that. You want to make sure your output type is a Windows runtime component. By changing your class library's output type to a Windows runtime component, it actually has some other repercussions as well. So what it now forces you to do is that all the code that you're writing inside your background task must be compatible with Windows runtime concepts. And so some things are not fully compatible with them. For example, LINQ. When you compile LINQ, the code is not, you cannot generate Windows runtime component code for that. And so you don't have to know about this. It's as soon as you use LINQ inside your background task and you compile, you'll pretty much hit errors and say it's that, which will tell you that this is not Windows runtime compatible. So that is some drawback. And that's pretty much it. That's your background task. So I have a ready-made project here that I already implemented a simple background task in there. And inside the background task, I'm going to show you how to use your background task builder. And background task builder is basically a builder model that we use, a builder pattern that we use to register background task. In that you provide your task point, in that you provide a class name, which is the background task entry point. You have to provide a name. This allows us to identify what your background task is. You have to provide a trigger, because if you don't have a trigger, what is your background task running for? And then you may provide a conditions if you care. I am using the internet available condition here, but that's not really required. And that's it, and then you just call register. The other interesting thing here that you should pay attention to are these two things: the completion and progress callbacks. These are callbacks that are provided to the app that your background task runs, so that your foreground app can actually show progress. For example, if your app is in the foreground and your background task is running, you may want to show progress. So for example, if you're downloading your mail or you're downloading your RSS feed, you may want to show some progress on your app, like downloaded 5 new feeds, downloaded 10 new feeds. So the progress allows you to do this. The thing to keep in mind, though, is the progress is only delivered if your foreground app, if your app is in the foreground. Because if your app is not in the foreground, or is suspended or is terminated, there's nobody listening. And so the progress and completions are never delivered. And that's the other thing that you want to keep in mind. Since a background task can run, even if your app is suspended or terminated, you have to store state, you have to exchange state using persistent storage. So over here, if you look in my background task here, you will see that I'm actually storing some content inside the application data. This allows me to know that this background task ran successfully, because otherwise, how will the app ever know that the background task ran successfully or not, if it's suspended or terminated? And so that's pretty much it. And to run this background task, you just let's just launch it, register, and we've registered the background task. And let's trigger the background task. And if you use the drop down from here, it'll show you the background task it'll show you the name of the background task, which is test class. And let's click that. And if you quickly go, you missed it. Anyway, that's what happens in demos. So the thing that I wanted to show there was when your background task was running, I was trying to show progress here. So all I did in this background task was a pretty I is equal to 0 to 1 to 1 million, and I was updating a count. And when the count reaches a certain value, I was updating progress. And that progress was basically going to be done here, was going to be displayed here. And it happened so quickly that it didn't show up. Maybe we can do it again. But okay, so that was the point I was trying to make. Progress and completions are only delivered when your app is in the foreground. If your app is not in the foreground, then those progress and completions are not delivered. And that's it. That's a basic demo of a background task. And so this is just some basic code of a background task. This is how you register background tasks. I already talked about it. You have a builder class, which follows the builder pattern, and you need to provide a name in there. You need to provide your entry point, which is your class name. you need to provide a trigger, and you need to add 0 or more conditions. And then you need progress and completion handlers as well. And this is your basic background task run method. The thing that you should remember that is interesting to see here is that a background task must have a cancellation handler. If you don't have a cancellation handler, then when the system tries to cancel a background task and you don't have a cancel handler, we will terminate your app because nobody's listening. And you don't want that, because if you get terminated, you could have data loss or corruption. So you should always implement a cancellation handler so that you can cleanly unwind from a background task if you have to cancel it. And this is a sample manifest. You don't have to take down any of this code. I have links to our sample project at the back of the slides, which has all of the background tasks implemented, and you don't have to take down any of this code. The thing to note here is that if you do use a trigger that requires lock screen, you will have to implement lock screen elements as well. For example, a badge icon and detailed text. And the sample project that I linked at the end also has examples on how to do a lock screen app. So debugging a background task. So one of the most common complaints that I've seen from developers is that I don't know why my background task is not running, and I did all the right things, but I cannot figure out why it's not launching. And so to help with those scenarios, what we have is we have a lot of debugging information inside our background task event viewer channel. And in addition, in Windows 8.1, what we did is we added a whole bunch of management interfaces as well, PowerShell commandlets. And these PowerShell commandlets allow you to enable debugging on background tasks. It allows you to see how much resources your background task has used, and even launch or trigger background tasks or delete background tasks. So let's do a quick demo on debugging a background task. So here's a background task, and the actual class name, if you look at my manifest, is background task class 1. Is background task class 1. However, I have a typo in my code, and in my code it says class. It should say class 1. And so when I try to launch this app, or when I try to launch this background task, it won't run if it launches. Okay. So we registered the background task, and now let's try to trigger the background task. Cannot activate background task. And now you don't really know why you can't activate background task. It just says cannot activate background task. So now if you go to the background task event viewer channel and hit F5, we actually have some debugging information in our operational channel. And in our operational channel, you will see that the entry point of the background class is class instead of class 1. So this is more of a very contrived example, but in a real example, it won't be so obvious. You'll have to think about it a little bit more. We also have another diagnostic channel in there that has more copious amounts of debugging information. So this is more useful if you really want to go deep into figure out why your background task is not running. But this should basically give you an idea of why this thing is not running. And then if you change that, it'll start running. And that's the short demo. Some common gotchas. I'm not going to read through all of these gotchas. The one thing that I would like to call out in there is the close. Inside a JavaScript background task, you must call close, because if you don't to indicate that the background task is done. If you don't call close, then it means that we don't think the task completes. And so we will keep your background task running in the system. It will be consuming resources. It will be consuming CPU and memory. And so you must call close in your JavaScript run method for us to know that your background task is done. In Windows 8.1, this is now a WAC failure. We added a WAC test that actually verifies if you called close or not inside your JavaScript run method. And so in 8.1, we've improved the situation so that you actually get a WAC failure. Connected standby. So connected standby, also known as always on, always connected. This is a state of the machine, or a hardware state where the CPU is in extremely low power mode. And when it's in this low power mode, what happens is that the system is still connected to the network. And you can still download your email, you can still receive your phone calls. However, However, all of the code is still not completely running when it's in connected standby mode. For example, we throttle various things, we suspend desktop services, and we also modify some of the timers in there so that not a lot of code is running in connected standby. The only way for you to run code in connected standby is through, for a store app, is through background tasks. And that's basically what is happening here. So this is a surface, and this surface is now in connected standby mode. And if I hit the power button, you will actually see that looks like I got 17 new mails. And 17 new mails basically are background tasks that ran. So this system is in connected standby, and the mail background task ran, and it was syncing my email while it was in connected standby, and it updates the badge tile to show how much new mails I got. So it looks like I got a lot of mail while I was giving this talk. And when a background task is running in connected standby, we bring the system out of low power mode. The system is, and because you're trying to run code, so you can't put the CPU in low power mode, otherwise your code just won't run. And if your background task uses network, we also bring the network out of low power mode. Usually when a system is in connected standby, the CPU is in low power mode and the network is in low power mode. We call it network quiet mode. And if we know that a background task is using network, we even bring the network out of low power mode. This is a power optimization that we do because we don't want to bring the network out of quiet mode if you're not using the network. Otherwise, you're just burning power unnecessarily. And if you want to see all of the stuff, all of the background tasks, or all of the activity that is happening in connected standby, we have a utility in there in System32 called powerconfig.exe. And if you say powerconfig.exe/sleep study, it'll generate an HTML output. And the HTML output page contains a list of all the background tasks that ran while your system is in connected standby. And I have an example of the sample HTML output there. So it'll show you an entry point, it'll show you how much time was spent in that background task, and all of that stuff. So power comes with responsibility. What we've noticed is, based on our telemetry, is that, so like I mentioned, when background tasks are running, we bring the system out of low power mode. This obviously has impact on the battery life of the device. So for example, if there is no activity, this could stay in this connected standby mode for a really long time. But if you have more activity, the system cannot stay in connected standby mode for the same amount of time. So what we've seen is that developers, when they use background tasks, they forget to use the internet available condition. And if you don't use the internet available condition, we don't know that your app needs network. And because we don't know your app needs network, we don't bring out the system out of network quiet mode. That means if you try to do any network activity, your background task cannot make any network calls. And so if you try to talk to Bing.com or Google.com, your task is just sitting there waiting for a response. And if you're sitting there waiting for a response, not making any forward progress, the system is out of now low power mode. The device is now fully consuming battery and power, but nothing is really happening because your background task is just sitting there doing nothing. And so as we saw people using background tasks, this was a pretty common mistake. And so we implemented something called idle task detection. And basically, idle task detection is the background task infrastructure keeps track of whether a background task is really using CPU and network or not. And if it's not using CPU or network, we send the background task a cancel notification. And now here comes the second gotcha. A lot of developers don't even use a cancel handler. And so if you don't use a cancellation handler, when we try to cancel you, nobody's listening. And since nobody's listening, we terminate the app. So this is bad for the app, right? Because if you just terminate the app, it doesn't let you cleanly unwind. You could have data corruption and all of those things. And it also generates a Watson error dump. And this error dump is sent to your developer account on your store, which is also bad for your app because it'll be clearly visible that an app foo has a lot more crashes. So that is also bad for you. So please use a cancel handler. So this is a common paradigm that we document for developers. If you have inside your background task, if you have a bunch of async operations, what you should do is you should associate a cancel token, the same cancel token with all of your async operations. And if we have to cancel your background task, inside your cancellation handler, you simply call cancel on your cancel token, and this will unwind all of your async operations. Even if the async operation is waiting on something, it'll get canceled and your task will cleanly unwind. In JavaScript, there is an equivalent where you have a chain of promises, and when you call cancel on the chain, all of the promises are canceled, and your background task can cleanly unwind again. So you don't have to take down this code. It's fully published on MSDN, and you can just look at the MSDN for this. Resource constraints. So as I've mentioned throughout the talk, and I'm sounding like a broken record, the whole background task infrastructure is designed for power awareness. It's designed to be power efficient. And so that's why we have resource quotas. We have CPU usage quotas, and we have network usage quotas. And the interesting thing here is most people don't think of usage. We say a background task has 2 CPU seconds. And most people don't easily understand what 2 CPU seconds means. Most people are used to say, my task gets 5 seconds of wall clock time, because that's much more usable, right? Time on a wall clock scale is much more easily understandable versus actual usage. But there's a reason why we chose usage. Usage is more fair. For example, let me explain what that means. If you're writing a background task and you have code that says download data from Bing.com, for example, when you're downloading data, your task is not doing a lot of work. It's just sitting there waiting for a response. So if you look at an actual thread, most of the time is spent waiting, and the thread is not doing any work. And so if the thread is not doing any work, we don't want to charge that amount of time to your app. And so we only charge the amount of time that you're actually using the CPU. And that's why we use CPU usage quotas and not actual wall clock time. So it is a more fairer metric. And the other feature of resource quotas is we have something called global pool. A global pool is basically a pool of CPU and network quota where apps that are allowed to run in the background can take resources from. And the reason we implemented this is that, as you can imagine, having resource quotas can be somewhat hindering to provide good user experience if you need to do a lot of work in the background. So there might be cases where suddenly on a day you might receive 25 new emails. And if you receive 25 new emails, whereas on your average day you pretty much only get 1, you might run out of quota. And since you run out of quota, we don't want you to immediately get suspended for these sorts of bursty activities. And so to handle these kinds of bursty activities, what we have is a shared pool. And inside the shared pool, your app receives a certain amount of quota, and it can automatically run, even though it finished its guaranteed CPU, 2 CPU seconds. And all of this is completely transparent to you. The app developer doesn't even know that his app is using global pool. And as soon as he finishes his app quota, the system will notice that, hey, this app has finished its quota. However, we still have all of this pool in here, and the app still wants, and the background task still wants to run. So we'll just give him some CPU or network, depending on whichever resource they've consumed the most. And the other concept that you should know about for background task resource constraints are critical background tasks. So as you can imagine, one of the main users of background tasks are VoIP apps. And so if you're receiving a VoIP call in the background, we don't want the VoIP call to be suspended because you ran out of quota, because then the user won't be all that happy, right, if he's like receiving a VoIP call and we suspend him in the middle. So a VoIP background task is marked as critical. And if an app is implementing a lock screen call capability, we know that it is doing a VoIP call. And when a critical background task basically means it always receives the guaranteed amount of quota. So anytime you launch a VoIP call, it always receives 2 CPU seconds. So these are the guaranteed amount of resources that a critical background task receives. So these are the resource quota values. I'm not going to go into the quota values because they're all published and documented on MSDN. The thing that I would like to call out in there is on the left side. In 8.1, we've added PowerShell commandlets, and those PowerShell commandlets actually allow you to see how much resource quota you've used. So you can run your test, you can do your work in the background task, and you can use those PowerShell commandlets to understand how much CPU and network you've used. The other thing that I would recommend you should also do is you should test your app by disabling global pool. Like I already mentioned in the previous slide, if global pool is completely transparent to you, so while you're testing, you may not even know that you're actually relying on global pool so heavily. But out there on your customer system, since the global pool is a shared resource, some other app could have finished all of the global pool and you have nothing. And so if you always rely on the global pool, you may not even finish your functionality. So make sure you test by disabling global pool. This will allow you to understand what is the actual behavior of your background task. Finally, so what's new in Windows 8.1? So in Windows 8.1, we haven't added a whole lot of stuff inside background task. We added a few new triggers that you already know about. We tried to round out the developer experience. We've invested a lot in partial commandlets and making things easier to debug. The one new feature that we've added, though, is quiet hours. And I'm going to do a quick slide on what quiet hours are, and try to explain to you why it's useful here. So quiet hours is basically it's basically a time that we set out of the box from 12 a.m. to 6 a.m. in the morning, where we say no background activity can happen on the system. And other than background activity, we also don't allow any notifications. So there are two caveats to this. We will continue to allow VoIP calls in the background, even in quiet hours. And any alarms that you set, they will continue to fire even in quiet hours. Of course, there is a setting in here for you to disable VoIP calls if you so desire. You can go to the PC settings, and under the PC settings, you will see quiet hours in there, and then just disable VoIP if you don't like VoIP. The other thing to know about quiet hours is that when the user is actively using his machine, we don't engage quiet hours. So that means if you're awake at 3 a.m. in the morning and you're using your device, we don't engage quiet hours. So your email can continue to sync, your VoIP calls will continue to come, your RSS feed will be updated. So we don't engage quiet hours while you're actually using the device. When the system enters quiet hours, we cancel all currently running background tasks. And any background task that is fired or triggered while the system is in quiet hours, that is queued up. We queue it up in our database, and when the system exits quiet hours, we release that background task so that it can start running. So typically for your app, most of this is completely transparent to you. You won't even know that you need to do something special. You'll receive a cancel notification on entry, and then if your trigger expires, it'll basically be buffered, and we'll launch it when we exit quiet hours. So this is pretty useful, I think. So I don't have a lot of time, but I wanted to point out one of the reasons why we implemented or designed this feature is that when we looked at our customer telemetry on connected standby machines, what we saw was there was a lot of background activity, spiky background activity. And to obtain really good battery life or really good long amount of battery life, you want a steady period of low power state. You don't want the system or the CPU or the network to keep coming up every few minutes, because that will be bad for your battery life. So what we did is we implemented this quiet hours, and we chose some default values, 12 a.m. to 6 a.m., where we thought most users are not really using their machine, so let's just not allow any background activity in here. So now out of the box, if you take a Windows 8.1 machine, you will have a solid 6-hour chunk of period where there should be no background activity, which is going to be pretty useful from a battery life perspective if you have a connected standby kind of device, Surface, for example. So other background task updates. Triggers, I already talked a lot about these triggers. The one trigger I haven't talked about is the background work cost trigger. This is a new trigger that is part of the system trigger. This is a hint to apps that says that, hey, the system is in, the conditions of the system are such that you probably don't want to do a lot of work, or you probably want to do a lot of work. So if you're on AC, for example, we publish a background work cost of value equals low. So that means you can probably do a lot more work now because the system really is in relaxed state. It's on AC, so there is no battery impact right now. And the other thing that I also haven't talked about is we've added a new property called cancel on condition loss. Remember I had mentioned a background task can have 0 or more conditions. Now, there might be use cases where you probably don't want to do work when some of those conditions changes. For example, if you have a condition called internet available, and if your machine or device goes through a tunnel, you lost the internet connectivity. So at that point, you probably want to just cancel and unwind your task cleanly. But you probably can't do that easily, right? Because you're already doing the async operations and you're waiting on the network, and so you're just sitting there. And so it's not easy for you to unwind cleanly. So what we do is if you set this property cancel all condition loss, when we detect that the condition has changed, we will cancel your background task automatically. So if you use an internet available condition, and you go through a tunnel, and you set this property, we notice that, oh, you're now in a tunnel, and there is no network connectivity anymore. Did any background task use this new property called cancel on condition? Aha, it did. And so we go and figure out what that background task is, and we go cancel you. This allows you to cleanly unwind your task without doing any real work. You don't have to do waits. You don't have to check anything. So it's pretty useful. Again, it's the same, continuing our theme of conditions. And do's and don'ts. I am not going to talk a lot about this, mostly because we're pretty close to the end. The one thing I would like to call out here is that you should always design your background task to be decoupled from your foreground app. As I mentioned like multiple times, a background task can run even if your app is suspended or terminated. So do not rely on your app to be around. A background task should be decoupled from your app, and it should use persistent storage, files, application settings, to share any sort of data, because you will not be able to talk to the app. It might be suspended. And the rest, and one other call out, you should always use cancellation handler, because if you don't use the cancellation handler, your task cannot cancel itself if we have to cancel your background task. And if you don't have a cancel handler, we will terminate your app, which is again bad for your app, because you don't want to be rudely terminated. Related sessions. These are a few sessions that have somewhat related contents. Craig Broxman's session on Live with Activity talks a lot about tiles, notifications, and all of those things. And the Bluetooth talks about some of the device triggers that we mentioned. Fast and Fresh apps also talk about some of the background task related style contents. And Windows Runtime Internals is just an interesting talk, I think, which if you are kind of geeky or nerdy and care about the internals, that might be an interesting talk for you to go. And that's pretty much it. So I'm here for questions. I'll be here after the talk also, so feel free to catch me and ask all your questions. Thank you. Wait.